Welcome to lecture 17. Last class we had a rune and we learned all about Rolle's theorem and the mean value theorem. So I'll assume that you understood that pretty well. Let's go over the homework. What did I give? Did I give you guys any related rates problems or no?
Nope.
Okay, I'm going to over the weekend. So then the homework was only on the mean value theorem. Is that correct? And finish that packet on implicit differentiation. How's that going? That packet on implicit differentiation.
Good.
Okay, good. Because I'm not going to go over it. So. The homework on the mean value theorem. Let's begin. How did this go? What'd you say?
Wait, number 4.
Yeah, can we do number 4? Well, yeah.
We can do a bunch of them right now. Today is also kind of all about the mean value theorem. It's about what you can do with the mean value theorem, which is a lot of stuff. So what was the homework? Can someone?
Page 216.
Yes.
Number 1, 4, 7, 19, 24, 25, 44, 50, 65, 66, 69, 71.
Okay. Awesome. Alright, so we will talk about. Oh, interesting. It does not apply. So.
66.
66. Oh, this is the sports one. Well, that's actually kind of a slightly dumb problem.
What?
65 is very interesting and important. Shall we do 150? 50, yeah. And maybe like one more? 71 was exactly like what you did in class with the rune, right?
Yeah.
Like, I don't think we need to go over that, do we? 24. We can certainly do that. All right, maybe we'll add one as we go, but let's just start now. Number 4 is a strange problem. It said, explain why Rolle's theorem does not apply, even though we have a continuous function on a closed interval. The function was expressed sort of awkwardly as the square root of 2 minus x to the 2/3 to the 3/2. Well, or actually it was just written like that. But that's the same thing as 2 minus x to the 2/3 to the 3/2. Alright, so what does this function look, oh, and they wanted this, they were asking about this function on the interval -1, 1. Alright, well, I mean, I don't know what to say. I guess one thing we could do is we could just say, so they say explain why Rolle's theorem does not apply. Well, what must be true in order for Rolle's theorem to apply? Yes.
It has to be continuous and differentiable.
Has to be continuous and differentiable. Is this function? Oh, and f of a has to equal f of b. So maybe we should just quick do that first. What is f of -1? Well, -1 to the 2/3 is just 1, so this is just 2 minus 1 is just 1, right?
Yeah.
As is f of 1, because this is pretty clearly an even function. But Rolle's theorem does not apply basically because it's not differentiable. It's not differentiable at 0. How do I know that? I kind of just know that.
No, how do you know that?
How do I know that?
Am I supposed to go through and test everything?
We just take the derivative.
I guess we could just take the derivative. So if we take the derivative, we could try to do this at least. Let's see what happens. So I get 3/2, 2 minus x to the 2/3 to the 1/2 back inside for the derivative of 2 minus x to the 2/3. And what is the derivative of 2 minus x to the 2/3? Well, it's -2/3 x to the -1/3. Stop me if I did something wrong, but I don't think I did. You agree? Okay. So just to clean this up a little bit algebraically, let's see, the 3/2 and the 2/3 cancels, leaving a -1 residue. So this is basically the square root of 2 minus x to the 2/3 over, and there's a negative, over the cube root of x. So there's my derivative, and everything's, fine and all, but if you look at this at this derivative function, it clearly is just undefined at 0. I mean, that's probably the simplest thing to do, right? Satisfied with that, Giovanni? Undefined at 0, so f prime of 0 does not exist. Since this function is not differentiable at 0, it doesn't satisfy the mean value theorem, or it doesn't satisfy Rolle's theorem. And I think, let's see, are we smart enough to figure out actually what this function looks like just by being smart? Maybe. Because what is 2 minus x to the 2/3? Well, y equals 2 minus x to the 2/3. I know what 2/3 looks like. What's 2/3? 2/3 is the bird. X to the 2/3 is the bird. So this is upside down bird up 2. So upside down bird up 2 means that it's going to look kind of like this, right? You guys following this at all?
Yeah.
Okay, good. So that's that function, and it's just pretty obviously not differentiable at 0, right? Because it's sharp pointing. It's upside down bird plus 2. And then we're taking that to the 3/2. So if we're taking that to the 3/2, I think I might have done something wrong here. Did I? 2 minus x to 2. Oh, on the interval -1, 1. Yeah, so it's only this little piece from -1 to 1 that I'm interested in. So I don't have to worry about things being positive and negative. So it's really just that. It's upside down bird with clipped wings. Or just maybe small, just a small bird. So that's a little bit nicer. It's like a parakeet. And so what if I raise that to the 3/2? I'm not really sure what the hell that's going to do exactly if I raise that to 3/2, but that pointy bit is just still going to be pointy. Let's move on. All right, good. 24 is a just straightforward, at least theoretically, Rolle's theorem problem. It just says, hey, is Rolle's theorem applicable? And if so, please find the points that satisfy Rolle's theorem. All right, the function is f of x equals cosine 2x, and it's on the interval -π/12 to π/6. Okay, first off, is this function continuous? Of course. Is it differentiable? Of course. What is f of -π/12? Well, that would be times 2, so it would be cosine (-π/6). Cosine of (-π/6) is √3/2. What is f of π/6? That is
Cosine?
Yeah, but the thing is, there is π/12 is in the interval.
Wait a second.
What?
Okay. Anyway, cosine of π/3 is 1/2. So this is just Rolle's theorem. It just
Does not apply.
It just does not apply here.
π/12 is in the interval, if you don't do like a smaller interval.
I guess. Determine whether Rolle's theorem. No, but it specifically says, can Rolle's theorem be applied to this function on this interval?
I read it as in, so.
I don't know. I think this is just a stupid question.
It just asks if it applies or not, and it doesn't.
I say it doesn't. Yeah, I say it doesn't. It doesn't for this particular interval. It does not apply because it's just in order to apply Rolle's theorem. I guess what it was trying to do is maybe it was trying to trick you because suppose we didn't notice this because we were being lazy. So if we were lazy and we didn't bother checking whether f of a equals f of b, then we would be like, oh yeah, we can do this, and then maybe this whole thing would go wrong. Does it go wrong?
Yeah, except as a student, the lazy thing to do is check every way possible to make this.
No, but is the derivative ever 0 on this interval? That's my question.
When x is 0.
Yeah.
When x is 0.
Yeah.
The derivative is -2 sine
Alright,
2x.
so
So sine of 0.
I just don't like the problem. I will never sign it again. 50. 50. Hey, Mr. Hammond.
Hello.
50 is this function 2 sine x plus sine 2x on the interval 0 to pi. And here are the directions. Determine whether the mean value theorem can be applied to f on the closed interval. If so, find all values that satisfy the mean value theorem. All right. Well, can we apply the mean value theorem? Yeah, we can. This is a continuous and differentiable function. So we just take the derivative, or maybe first we can just compute what the slope should be. So what is f of 0? F of 0 is 0. And what is f of pi? This is another boring problem. F of pi is also just 0, right? so that means that f of pi minus f of 0 over pi minus 0 is just 0. And so basically we want to see, is there anywhere on this, yes?
Wait,
Did I mess up? I don't
it's
think so.
using the mean value theorem, so do you not have to check that?
It says, is the mean value theorem applicable? And it is applicable because it's continuous and differentiable.
But you do have to check that. Do you have to check the
I checked it only so that I could compute this,
Oh, okay.
right? Because the mean value theorem says, you know, by, maybe I'll just write this out. By the mean value theorem, there exists a point C on the interval 0 pi such that the derivative at C equals f of pi minus f of 0 over pi minus 0.
Okay.
That's just what the mean value theorem says, right? So I just did a little side calculation to see what those were. It turned out that they're the same, so actually we're just looking for a place where the derivative is 0. That's really all that's going on. Do you need to talk to some juniors or something? Is this Puzzlepalooza related?
I just want Flannery and Calvin to sign up.
Flannery sort of doesn't exist.
Maybe.
Calvin's right here. You want to go talk to him?
No, I don't need to talk to him. I just told him what I need to know. He needs to
Calvin,
sign up.
Puzzlepalooza, sign up for Puzzlepalooza.
Prizes
Or,
are huge.
or study hall if he wants to be, completely lame. It's
Okay, good.
Thanks. I shouldn't say that. Maybe he wants to be completely lame, and I just, now I'm bullied.
Lose cover. Yeah, that's a little bit of bullying. It's okay.
It's not worse than Mr. Rose though.
Okay. Good. I think Busis, you do more bullying than I do.
Okay, this is worse than me.
Okay. So anyway, we're back. So basically, it's like, can I differentiate this and set it equal 0? Yeah, I can. This is going to be 2. Derivative of sine is cosine, and the derivative of sine 2x is cosine 2x back inside 2. So now I just need to see when this is 0. I can divide by 2. So I have cosine x plus cosine 2x. Now what? This is just really testing your this is just testing your pre-calc B knowledge. Yeah. What is cosine 2x? It's 2 cosine squared x minus 1. Now we have something which is quadratic in cosine.
Let's say quadratic.
So I just factor. So this is 2 cosine x 1, cosine x 1, and yeah, the assumption is that you know your trig. 2 cosine squared. Let's see. What is that going to be? Plus 2 minus 1. That works.
Yes.
And thus this will be 0. It will be 0 whenever cosine x
It's 1 half.
equals -1 or cosine x equals a half.
Why'd you switch?
What's up?
You switched them. Sorry, it's OCD. Like you put the.
Oh well. So this is going to be at pi, and this is going to be at pi over 3 and 5 pi over 3. Are either of those or any of those on this interval? Yeah, I guess just that one is, right? So there's my guy. So at pi over 3, the derivative is 0.
Wait, are you not allowed to put the
On a pi.
I don't know. I think it's the mean value theorem says somewhere on the interval.
Oh.
I don't know. So good. Let's do 2 more. 65 and 60. You want to do one more normal problem, or are we feeling okay with this? I think we're okay. Let's do the 2 weird problems. They're both kind of have some thinking to do with them. 65. This is the bicycle problem. 2 bicyclists begin a race at 8 a.m. They both finish the race 2 hours and 15 minutes later. Prove that at some time during the race, the bicyclists are traveling at the same velocity. Talk to me. Yeah.
Okay, so I did the thing where instead of graphing their velocities, you care about the difference in their velocities, and when the difference is 0, then you know that's the same velocity. So you know that in the beginning, the difference in the velocities is 0 because...
Yeah, wait, okay, hold on. Okay, yep, I totally agree with you. So, this is an interesting problem, right? Because you have 2 guys on bikes. How do you draw a bike?
Wheel.
Something like that.
No.
Here's another. That's not a bike.
That's not
All right, and they both start the race at 8 a.m. and they both finish. Let's call it 2 hours and 50 minutes. That's like 130. What is that? 135 minutes. Yeah. So they finish 135 minutes later. So let's just call this time 0, time 135. So they both finished at the exact same time, but who knows how the race might have happened, right? This guy might have gone really, really fast and had a flat tire, and then he caught up and passed him, and then he...
There's not even a person on that bike.
It looks...
The center one.
It's like one
No,
of
the
those
second
recumbent
bike.
bikes where you
Second bike.
sit backwards.
Anyway,
It doesn't matter. It doesn't matter. So they might be passing each other in all various different times, but eventually they end the race at the exact same time. So prove that there was some point at which they were going at the exact same velocity. So what Yael says is pick different functions to represent the positions of the two guys, right?
Yeah.
Yeah. So let f of t be the position of biker 1 over time, and let g of t be the position of biker 2 based on time t measured in minutes, where t equals 0 is 8 a.m. Is this kind of clear? All right, now comes the key insight. Say it one more time.
So then you have another function that's like f of t minus g of t.
Yeah.
And you want to find when that is equal to 0, because that means that it's the same.
When their derivatives are.
Sorry, when the derivative is
Mhm.
equal, the
Yeah.
velocities are the same.
Yeah, you kind of just are reproving the mean value theorem proof that we had, sort of, right? You're saying, all right, what is h of t? She says let h of t be f of t minus g of t. In other words, you define a new function to be in the gap in the positions of the two bikers. And what is h of 0? Well, h of 0 is just f of 0 minus g of 0. Where are they at time 0? They're in the same position, so their gap is 0. Where are they at time 135 for measuring in minutes? Or what is h of 135? Well, it's f of 135 minus g of 135. But by assumption, they finished the race at the exact same time, so their gap is also 0 there. And now?
And now by the mean value theorem of h of t, if it's
Yeah, I guess maybe it makes more sense to just apply Rolle's theorem here, right?
Yeah.
Because
I did it a little differently.
oh, you did it differently than this? I thought this is more.
Same, yeah,
Same
I
kind
didn't
of
do it
thing.
formally.
Yeah, so then you just apply, if you now apply Rolle's theorem to h on the interval 0, 135, assuming that these two bikers have continuous and differentiable position functions, then the difference is also continuous and differentiable. By Rolle's theorem, they have the same y value. So if we apply Rolle's theorem to h on this interval, what that says is that there exists a point C on the interval 0, 135, such that h prime of C is 0. Ruben, it's like exactly our proof of the mean value theorem, right? It's really just you guys doing it all over again.
Just
And then on the other hand, h prime of C, or h prime of t, is just f prime of t minus g prime of t. And so if h prime of c is 0, then h prime of c is 0, which is f prime of c minus g prime of c. And our conclusion is that f prime of c equals g prime of c. So what you guys did roughly, did you recognize it was more or less the same thing? Can you raise, okay, cool. Cool. How about, there was one other problem, you guys want to talk about number 66?
Yes.
Okay, so, yikes. So 66 is this problem that says this car like accelerated pretty quickly, right? So these numbers are a little bit gross. At 9:13 a.m., a sports car is traveling 35 miles per hour. 2 minutes later, the car is traveling 85 miles per hour. So at 9:15, the car is traveling 85 miles per hour. Prove that at some point during this 2-minute interval, the car's acceleration is exactly 1,500 miles per hour squared. All right, first of all, there's like a giant warning flag that needs to go up. The warning flag.
Miles per hour
Yeah,
versus
like
hours.
Oh, miles per hour versus minutes.
Yeah, units. Bad units are happening. We have mixtures of minutes and hours. So you want to do this whole thing in hours or in minutes?
Hours.
I think hours, right? So what we really have is a situation in which we're going 35 miles per hour, and then the relevant number is
1/3.
2 minutes is 1/30th, yeah. So 1/30th of an hour later, 1/30th of an hour later, we're suddenly going 85 miles per hour. Well, one way of stating the mean value theorem is that over any interval, the average rate of change equals the instantaneous rate of change somewhere, right? There's somewhere on the interval in which the instantaneous rate of change equals the average rate of change. So what is the average rate of change of the velocity, otherwise known as average acceleration? Is this making sense?
Yeah.
Okay. The average acceleration, which is just the name for the average rate of change of the velocity function on the interval from 0 to 1/30th is, well, it's simply my velocity at a 30th minus my velocity at 0 over 1/30th minus 0. Someone see what I'm doing?
Yes.
Just computing the average velocity. All right, so I can just do this. Well, it's just 85 minus 35, so that's 50 over 1/30th, and there it is. It's 1,500, and the units are miles per hour, right? Because I'm dividing speeds, I'm dividing velocities in miles per hour divided by a time unit. Is everyone kind of cool with the units? All right. So that is the average rate of change of the velocity over this time interval, and the mean value theorem basically says that at some point on that interval, the instantaneous acceleration must equal the average acceleration. So by the mean value theorem, there's some point at which I'm accelerating at exactly 1,500 miles per hour. Okay, are we good? Can I have this homework? Over there, we're going to do like a million more mean value theorem related things.
I got mine.
Wait, you never told us about the last one you said?
Next week, Thursday.
On what?
Everything we've done
Are they
since
going
then.
on the quarter?
Yes.
And then screen test?
Yeah.
Is it a full period test? There's like the other one. Yeah.
Because what tests are the hardest?
Somewhat about this, but I'll let you know about it. I'll put something in there, it'll be fine. Alright, yo.
Hey, get your water.
Yes. So. Alright, Eric. Mean value theorem, as I mentioned, important theorem, really deep. I think it's the second most important theorem in all of first semester calculus. And there's so many different ways of saying what the mean value theorem is. Well, on one level, it's just this simple statement that says there must exist some point such that f prime of c is f of b minus f of a over b minus a. That's like the simple math statement. What does it really mean? Hopefully Ruben talked about it. Does it really kind of mean?
You might want to retell it, because I
What?
made it up.
You made up what?
The Turnpike story.
Oh yeah,
Oh.
we
I
were
just said,
visiting
like,
my
it's
grandma.
You didn't connect.
And I couldn't make a graph that accurately depicted it, or
You were visiting my grandma.
Whatever. I feel like talking about it. We're moving on. So there's maybe like three different ways of really thinking about the mean value theorem. On one like very boring level, it just says that there exists a point C such that f prime of C is f of b minus f of a over b minus a. On a more intuitive level, the mean value theorem says that if you give me some function, then there is always a point at which the slope of the tangent line is parallel to the slope of the secant line. We're going to talk about that, right? So a geometric understanding of the mean value theorem is to say that, you know, if you take any closed interval from a to b and you draw this terrible picture, you draw the secant line, there's a place where the tangent line is parallel to that secant line. But maybe the best way to think about the mean value theorem is the one I was talking about a few minutes ago. It says that on any given interval, that there's a point where the instantaneous rate of change equals the average rate of change. What the mean value theorem enables me to do to me, in words, what the mean value theorem really says is, if there's any interval whatsoever, there's always some kind of special point. There's a special point which, in some ways, represents the function over that interval. If this is some function that's like, if this function is like, I don't know, whatever, it doesn't matter, let's just take position, right? Then this amount, this f of b minus f of a, this f of b minus f of a tells me the amount of position which I gained over that interval. And this represents, this b minus a represents the amount of time that it took. This point c is the special point which represents the function on that interval, in the sense that, were I going that fast for the entire interval, I would gain the same position as I had if I had done the function the way I actually did it. Alright, so with the mean value theorem, what the mean value theorem does is it gives us a connection between the derivative and a function. And what you will find is that the mean value theorem is at the heart of every single time you try to conclude information about a function based on information about the derivative. Alright, here is a little example. So here's just an example. Suppose I tell you the following weird pieces of information. I tell you that f of 0 is -3. And, this is the other piece of information, that the derivative is less than or equal to 5 for all x. Alright, question. How big, and don't shout it out, how big can f of 2 be? Alright, think about that. Maybe make a picture, because that's how thinking happens. Oh yeah, and like it's continuous. Well, I already told you that the derivative is less than 5, so it's kind of like saying it's differentiable. And if it's differentiable, it must be continuous. So yes. Thoughts? F of 0 is -3. Calvin.
Wouldn't it be at 7 because since the biggest the slope can be is 5, if you assumed it was constantly 5 all the way until 2, you could say move up 5 for each move over to the right. So that would be 10 minus 3 or 7.
Yeah, pretty much, right? This is actually just common sense in some ways, right? We're saying, all right, here I am. I start at -3. I know something about the derivative. The derivative tells me how fast the function is growing. I'm not sure how fast the function is growing, but let's suppose that the function is growing, as this says, at a rate less than or equal to 5. The derivative is less than or equal to 5. And what that's telling me is that the rate at which the function is growing is 5 or less. And that kind of says, well, for every 1 I go over, the most I can grow over any unit of length 1 is 5. And I think what Calvin said is perfect. If the derivative has to be less than or equal to 5, then if I want to know how big f of 2 can possibly be, let's suppose that the function is growing at the maximum rate it's allowed to grow at, right? This is like a speed limit on your function. The function can grow at most 5. So then if it's growing at the constant rate of 5 for that entire interval, then it will gain 10 over that interval. And thus the biggest this function can be is 7. Does this make sense? Alright, bless you. However, I'm sorry, and that's totally correct, intuition-wise it's perfect. But to really prove this properly requires the mean value theorem. The mean value theorem is the crucial link between facts about the derivative and facts about the function. And what we can do is we can simply apply the mean value. So here's what we do. Apply the mean value theorem. Apply the mean value theorem to f on the interval 0, 2. What does the mean value theorem say about f on the interval 0, 2? Someone just say it. Kendall, just tell me.
That there is a mean value theorem. So there's a point, there's a c on 0, 2, such that the derivative at c is the slope between 0 and 2.
Yeah, okay. So f of 2 minus f of 0 over 2 minus 0. That's just a simple statement of the mean value theorem. Okay. But of course, so let's just keep writing. So that tells me that f prime of c has to be, well, f of 2 is the thing I don't know, right? But f of 0 I know is -3. So this kind of turns into f of 2 plus 3 over 2. Agree? Okay. So there is some point where this is true, but now what do I know about the derivative? Yeah. It has to be less than or equal to 5. So if the derivative is always less than or equal to 5, then this representative point the derivative at this representative point must be less than or equal to 5. And now suddenly I find myself in possession of some information about f of 2. Right? If I multiply both sides by 2, I get that f of 2 plus 3 is less than or equal to 10, and so f of 2 must be less than or equal to 7. Alright, I just provided a rigorous proof of the fact that this function can be at most 7 since the derivative is growing at rate 5. Cool?
Cool.
Okay, and this same kind of thing keeps coming up again and again. Alright, another thing which is sort of intuitively obvious, this actually turns out to be a really, really important theorem, and we talked about this at least once before. So we know this fact about constant functions. If I give you the function f of x equals k and I differentiate, like what do we get? 0. Yeah, duh. So check. The derivative of a constant function is 0. Alright, the converse is intuitively plausible, but nowhere near as obviously true. And that is that if the derivative of a function is 0, can I then conclude, I'll write question mark, that the function must be a constant function?
Yeah.
Yes.
Yeah, they're so sure. Why, Yo?
Because, like, okay, if the derivative is a constant function, like, yeah,
I mean, no, because